Today's video can be found on page 18 of your Unit 1B packet. You can see that it's the problem of the day. Please put in the values that are given in number 19 and 20. So when y equals 1, substitute that in for the y. 1 equals -3 times what x plus 1. So how do you get that equation to be equal to 1? And then when they give you the x value, y equals -3 times 1 plus 1. So solve those, 19 and 20. Write a linear equation for the relationship between the following quantities. So you need to know something about some measurements, and a hint, m equals how many k? So you're trying to find the constant that's going to go in front of this k. U equals the constant. What's the relationship between ounces and pounds? What's the relationship between meters and kilometers, hours and day, and so on and so forth? That's a little hint for that. And number 5. So finish that on your own. Pause the video. Work on that. Understanding linear equations with two variables. This is in the 8th grade text. So you might want to write that, the 8th grade text. This is video 10, and it's chapter 3, section 4. Write a linear relationship between kilometers and meters, n. We just had that. Here's a hint. See if you got it right. So a kilometer is 1,000 meters. A linear equation for n, the meters in terms of k, so meters, n, equals 1,000 times the kilometers. Did you get that correct on the page prior? A ball is dropped from the top of a building and the distance of the ball from the ground was measured. The results are shown in the following table. Write a linear equation for the relationship between time t and distance from the ground d. Well, the time is the independent variable. That's what you would put on the x-axis. And the distance it is, depends on how long it's been dropping, right? That's the dependent variable. We're going to talk about, and that would go on the y-axis. We're going to talk about independent and dependent variables. I'm keeping track of two things, an x and a y, or in this case, a t and a d. So at time 0, I have the ball up at the top of the building, which is 120 meters up. At 1 second, yes, it's getting closer to the ground. Now it's only 90 meters away. At 2 seconds, 60, 3, 30, 4. It hit the ground at 4 seconds. The height at which the ball is dropped is 120 meters. After that, the height from the ground is decreasing by 30. I can see this here. It's going down by 30 every time the seconds go up by 1. Down by 30, and the second goes up by 1. Down by 30, and the second goes up by 1. I'm making little carrots here. From 3 to 4 seconds is 1, correct? So putting the equation, trying to figure out the equation, the distance, d, is equal to the initial starting point, which was 120, and the rate at which it's falling. So we're going to talk about where did it start and what is the rate. It's going down at a constant rate. It's going down by 30 meters per second. Last year you called that thing the k, that rate, y over x equals k. Remember that from last year? Well, that's the rate at which the ball is dropping. So my equation has to have my initial amount in it, and since it's going down by 30, that's why there's that 30, times every second. So there's my rate, 30, -30, and here's my initial amount. So we need to find how we're going to be starting and what's the rate of change, what's the constant in the relationship. As a sand pit is being filled with sand, the height of the sand level in the pit was recorded. The results are shown in the table. So it's being filled, so it's going up, right? So the Time, again, is the independent variable. That would go on the x-axis because the height of the sand depends on how many seconds you're pouring it into leveling it up. So the dependent variable is the height of the sand. And every second that it goes up, the height, is it constant? It's going up by 2, going up by 2, going up by 2, going up by 2. Yes, every second has an increase of 2 centimeters per minute. The initial height of the sand in the pit was at 1 centimeter, right here, at time 0. And the sand level increases by 2 centimeters for every minute. The equation would be S for sand equals, the height of the sand is equal to the initial 1 centimeter plus 2 centimeters for every minute. 2 times the t, 2 times minutes. So here's my initial. Where did I start? There's my rate. The other way I could write this, because I like having the variable first, is 2t plus 1. I can just switch that order. So the height of the sand is equal to 2 centimeter increase per time, plus it started at 1 centimeter. That's what this equation says. Show your work. A drip coffee is collected by dripping water from a container on ground coffee and collecting the filtrate. The table shows the volume of water left in the container after making the drip coffee for t minutes. Write a linear equation for the relationship between the time t and the volume of water remaining. So I can see that, yes, my independent variable almost always is time here in these problems. And here's my dependent variable. The volume of water depends on how long it's been dripping. So it is decreasing at a constant, looks like it's going down by 2 every time. Yep, going down by 2 as the time goes up every minute. So my initial, what is my initial starting point? I had 50 cubic centimeters of water. So my initial starting point was 50. My rate, how is it changing? By exactly the same, is equal to -2 centimeters cubed, right? So it's going down by 2 cubic centimeters per minute. That's the rate. So it's -2. Now I'll put that into the equation using the variables that they've given you. So the volume left is my initial starting point of 50 minus 2 cubic centimeters per time. Number 21, a new bakery shop sells rolls for $2 each. Before noon each day, if a customer buys 2 rolls or more, they will receive a $1 discount. The table shows the cost C in dollars in terms of the rolls purchased before noon. So your cost, this is the dependent variable. This would go on the y-axis because how much you pay depends on how many number of buns you buy, right? So this is my independent variable, which is opposite the other examples that we've had there. The dependent variable is on the top now. My cost depends on how many I buy. That makes sense. Write a linear equation for the cost C. So we've got to find that initial starting point. I don't have 0 on my table here. Well, let's see if we can find the rate. Maybe that will help us get back to that initial. But I want to know when I buy no buns, what's my cost? I want the 0 to be here. The rate at which the money is going up. So it's going up, yep, $2 per roll, right? So we knew that because here it is right here, $2 each. That's my rate. And going up for a number of buns going up by 1, right? So my rate is $2 per roll, or just 2. my initial amount. So if I go down by 1 here, if I go down by 1, my cost is going to go down by 2. So I get a 1 and a 1. If I go down 1 more, I get my 0. And this is going down by 2. It would be -1. So if you buy no buns, you're getting the discount of $1. You don't have to pay the $1. That's kind of silly, but it is -1. They receive a discount of $1. So you're not paying anything really, and they're not going to give you $1 if you don't buy 2 buns. It's kind of a silly example, but that is the initial amount. So my cost equals $2 per roll, but if I go before noon, I get to take $1 off. Or I could write it the other way with my initial amount first, -1 plus $2 per roll. You could write it either way. This is the best form of that. Find the cost of 30 rolls that Mrs. Carmen purchased before noon today. So what is the cost if I'm going to buy 30 of them? Well, that's the number of buns, right? And minus 1. So it's 60 minus 1, which would be 59. So the answer is $59. And that's it for today's video.